Hello and welcome to this video on how to derive Newton's method with cubic convergence. Before we begin, I would like to start with a quick refresher on how to derive Newton's method with quadratic convergence. So in order to do this, we first begin with an initial guess, which we'll call p sub 0, and then we'll use the linear approximation for the Taylor series for a given function f of x around p sub 0. So that means that the second order term is going to be our remainder, so it's going to have a value of f evaluated at a point between p sub 0 and x. So once we have our linear approximation and our remainder, we will evaluate the function at the root, which we'll call p. So we replace x with p in our linear approximation for the Taylor polynomial. Now the remainder, it's going to be evaluated at a point between p sub 0 and p. And the whole premise of the Newton's method is that our initial approximation for the root, p sub 0, it's a reasonably close approximation. So that means that the term p minus p sub 0 is going to be small, like small enough so that we can neglect it. Which means that we are left only with the linear terms of this equation. Then f at p is 0 because a function at a root is 0, and then we are left with the polynomial in this form. Then we can use some algebra and we can simplify it the following way. So once we have it in this form, p equals p sub 0 minus f at p0 over f prime at p0, we can actually convert this into an iteration. So essentially what this means is that given an initial approximation, p sub 0, the result is going to be closer to p, to the actual root, an approximation to the actual root. So that means that we can rewrite this as an iteration. So then we have pn plus 1 equals p sub n minus f at pn over f prime at pn. So this is the Newton's method written as an iteration. Now, this is not a formal proof by any means, but we can say that the error decreases quadratically, and that's because the Taylor remainder, which is the term that we neglect, has the error of the function, p minus the approximation p sub 0, and it's a quadratic term, which means that for every particular iteration of this function, the error is going to decrease quadratically. Since we are assuming that p sub 0 is a reasonably good initial guess for the function, this term it's going to be less than 1 ideally. So as we know, a number that is less than 1 when elevated to the power of 2, it's going to yield even a smaller number. So the error is going to keep decreasing quadratically. This is just an intuition for why the Newton's method converges quadratically. As I mentioned earlier, it's not a formal proof by any means, but it's just a good like a good way to have at least an idea on how quick the function converges. If any of you wants to see a formal proof on the Newton's error convergence and the error bound, you can just leave it in the comments. And I forgot to specify that, yeah, this is between p and p sub 0. So now we'll see how to derive Taylor's method with cubic convergence. And we do this using the quadratic approximation for the Taylor expansion for a given function, instead of using the linear approximation as we just saw. So in order to do this, we'll evaluate fp around p0, same as we did before. So we just write the quadratic approximation for the Taylor polynomial that represents this function. Now, as you can see, the remainder is going to be the cubic term of this Taylor expansion, and it's going to be evaluated at a point between p and p sub 0. Now, following a similar intuition as above, we can say that the error decreases cubically, because p minus p sub 0 it's assumed to be small, given that we are assuming that p sub 0 it's a reasonably good approximation to the actual root. So as we assume above, this term is going to be small enough so that if we raise it to a power of 2 or the power of 3, it's going to yield even a smaller number. So this is enough evidence, to put it that way, to provide us with an intuition that the error term is going to decrease cubically for every future iteration that we have. And remember, this is all based on the assumption that p sub 0 it's a good approximation to the root. So now, since we neglect the remainder because we are using the quadratic approximation, we are left with these terms. Now, we can think of these terms as some sort of quadratic equation. So we can think as p minus p sub 0 as our x term, and then the coefficient of the quadratic term as our a, then our linear term as our b, and then our constant term as our c. And we can just write it as a quadratic equation, which means that we can use the quadratic formula to continue simplifying this equation. So after using the quadratic formula, we are left with the following equation. Now, we could argue that even though this approximation is correct and this simplification is correct, this is a naive approach. We can do better than this. We can, in fact, simplify this further so that it doesn't have a square root term and it's easier to compute. We'll see how to do that. Now, in order to continue the simplification, to make this an even better approach, we can take the f prime at p sub 0 squared out of the square root, and then we simply divide the remaining term inside the square root by f prime of p sub 0 squared. And we are left with the equation in the following form. Before continuing with the simplification, keep in mind that in order to get a good approach, since this is an iteration, we want p minus p sub 0 to be as close to 0 as possible, because the closer to 0 they are, the better that our approximation to the actual root is going to be. So we want to minimize this term. Now, simplifying the equation in the step before, like taking the f prime at p sub 0 out of the square root, will actually allow us to pick one of the two solutions for the square root, which will guarantee that this term is going to be the smallest term possible. To see how, we can see that here we have minus f prime at p0, and on the other side we have plus minus f prime at p0 multiplied by the square root. So here we have two possible solutions, and here we have a negative sign. In order to guarantee the minimum result possible, like the smallest one, we pick the plus sign. Because that way both of them will have opposite signs. So once we have picked the plus sign, we'll continue the simplification. This time we can simplify by just taking the common factor out. In this case, the common factor is f prime at p sub 0 over the second derivative of f at p sub 0. So we'll take that one out, and then this will give us like a more simplified version of the equation. So after taking that term out, we are left with 1 minus and then the square root term. The square roots are usually expensive to compute, and the fact that we have a square root also opens the possibility that we might have, complex roots, and that's not something that we want, at least for this approximation. We can simplify this further and get rid of the square root by remembering our initial assumption, which requires p0 to be close to the actual root. By remembering this assumption, we can see that this term inside the square root should be small, because if p sub 0 is close to p, then f evaluated at p sub 0, it's going to be close to 0. As a side note, during all of this derivation process, we are assuming that the first, the second, the third derivatives are not 0. The reason we are doing this is that this works only if the multiplicity at the root is simple. That means that if the multiplicity is 1. This procedure will not work, or will not be guaranteed to work, when the multiplicity of the root is greater than 1, as the normal Newton's method. With this in mind, we can continue our approximation. Now we can get rid of the square root by using the Maclaurin series expansion for the function square root of 1 minus x. Why the Maclaurin series? Because we are assuming that the term containing like all the derivatives inside the square root is going to be small, because p sub 0, it's a good approximation to the actual root. If it's small, that means that our unknown is going to be small, it's going to be close to 0. So an approximation around 0 should be a good enough approximation. So that's why we are going to use the Maclaurin series. It is also worth noting that this is a quadratic approximation for the Maclaurin expansion. So after we have written the Maclaurin expansion down, we simply replace this term inside the expansion and we get the following result. This result is going to give us the quadratic approximation for the square root term. So this is how we can actually get rid of that term inside our original equation. So now we just write our original equation and replace the square root with the term that we just computed. So after replacing, we just do like the usual simplification. We cancel the ones, then we have a minus. So if we have a minus, then we just invert the signs, and then we continue the simplification process. So then we take our common term and we multiply it by whatever it's inside the parentheses, and we are left with the following equation. We do the usual cancellations whenever we are multiplying. And after we are done cancelling, then we have a much compact version, or a much more compact version of this equation. Then, as we did above, we can actually write this in an iteration form. So we move the p sub 0 to the other side, and then we have that p sub 0 is our initial guess, and we do the initial iteration with our initial guess, and then here in this other side of the equal we have p, which is what we are going to get eventually. Which means that, as in with the derivation that we had at the very beginning using the linear terms of the Taylor expansion, we can also write this in iteration form. So we have p of n plus 1 is equal to p sub n, and then we write the rest of the equation that we got, and what we end up with is a much more compact and easier to compute version of the Newton's method, using the quadratic approximation of the Taylor series, which guarantees at least cubic convergence whenever we have simple roots in the function. This is way easier to compute than our initial naive approach with the big square root, and this is part of a family of methods called householder methods, which are really interesting and kind of provide us like a general form to write even higher order versions of the Newton's method.